Specialist with New York Sea Grant, and I'll be facilitating and hosting today's presentation, along with my colleague Hannah, who's behind the scenes. New York Sea Grant is a federal academic partnership between NOAA, Cornell University, and SUNY in New York State. We are one of 34 university-based programs under NOAA's National Sea Grant Program, and we function as a statewide network of research, education, and extension services supporting New York's coastal communities. So the map you see on the right shows where our offices are located throughout the state. I'm located in Kingston, right in the middle of the Hudson River Estuary watershed, which is outlined in blue on the map. And I serve the 10 counties that border the tidal Hudson River. My work focuses on coastal hazards, climate change, and overall estuary health, and is informed by the needs of the many stakeholders that I serve and the partners that I work with. And I worked with a team to make today happen. I want to give special thanks to Paul Malmros, Technical Advisor for the Hudson 7, for reaching out to our presenter today and having the idea for this talk. I also want to thank Dan Shapley of Riverkeeper, Kathy Nolan of Catskill Mountain Keeper, and Mary McNamara of the Lower Esopus Creek Advisory Council. So today's webinar is about extreme precipitation. According to the New York State Climate Impacts Assessment, New York has experienced increases in total precipitation and heavy precipitation events, and these trends will continue through the end of the century. So to give a sense of what we mean by heavy precipitation, the image on the right is of a flooded road in Palinville, New York, which is in Greene County, from a heavy precipitation event on December 18th, 2023. So some of you may remember that event. It was pretty big. And the image on the left shows that the location, the approximate location of where that image was taken, that it received an estimated 3 to 4 inches of rain that day. So heavy rain can lead to more flooding and affect water quality through increased runoff, which can contaminate water sources with pollutants, pathogens, and sediments. Beyond heavy rain, several types of storms are expected to happen more frequently and become more intense. And then adding to this challenge, experts agree that rainfall predictions based on historical data no longer capture the threats posed by extreme rainfall due to climate change. But as we'll see today, things are starting to change. Here in New York State, we want to highlight the Resilient New York program, which develops state-of-the-art stream studies to reduce flooding and build resilience in high-risk watersheds. As you can see on the map, the Hudson River Estuary watershed has had several studies completed that are available online, and the Lower Esopus, which is in the pink circle, will be undergoing a study hopefully later this year, which is very exciting. So if you're in that watershed, please keep an eye out for that kickoff meeting and any associated events. It's a great team that uses a process that engages the communities. So there is a survey at the end of this webinar. So if you want to try to be notified when that happens, we'll do our best to pass your information on to the right people. We also want to acknowledge the many organizations and dedicated individuals that are working on flood hazard mitigation, planning, technical assistance, and education throughout the watershed and the state, many of which are on the call today. And I'm very lucky to be connected to many of them through the Hudson Valley Flood Resilience Network, which connects local governments committed to taking actionable steps to manage current and future flood risks. And I'll describe that program in more detail at the end of the webinar today for those that may be interested. All right, so before we get started, please note that there will be time for questions after the presentation, and you can add them using the Q&A feature at the bottom of the screen. If you ask your question in the chat, there's a chance we may not see it. This is being recorded, and I'll send the link to the recording in a follow-up email. So without further ado, I'm very excited to introduce Dr. Art DeGaetano, who is a professor in the Department of Earth and Atmospheric Sciences at Cornell University and the director of the Northeast Regional Climate Center on Cornell's main campus. So we are honored to have him here with us today. So with that, take it away, Art.
Thanks, Jessica. Get on to my PowerPoint. Assume I'm sharing now.
Yep, looks good.
All right. So Thanks for that great introduction, Jessica. I guess I want to start off with saying I'm going to talk about some work that's really been a collaboration with a bunch of colleagues, both here at Cornell, a number of colleagues at Carnegie Mellon University that we've worked with on our extreme precipitation work. In term, also some colleagues down at the Rand Corporation and Rutgers. And then the credits go to basically all the organizations that have contributed in some way to our work in terms of funding. So you can see there's a wide variety from Virginia right on up through New York and in the Delaware River Basin, which is kind of going to be the focus of what I'm going to speak about today. So there's clearly been a lot of interest in looking at these changes in extremes in the future and basically how people can use them in their design and planning work. So real briefly, kind of how do I fit into the picture here? Like Sea Grant, the regional climate centers do come under NOAA. There's 6 of us across the country, and you can kind of see the footprint up there in the Northeast for our center here at Cornell, covering Maine down through West Virginia. And really why NOAA supports us and funds us is they collect lots of good data, but it's exactly that. It's data and tends to sit on servers and things like that. So really, we work with NOAA to make their data useful to stakeholders across our region. And really the way I look at it is it's changing data into information. So we work very closely with stakeholders. Again, going back to that credit list, what you will see is many of the people who have supported these projects are directly related to state DOTs or in Virginia, the New Jersey DEP was a supporter of our work as well as some river basin commissions. And I guess I should not leave out NYSERDA as well in New York State. So let's kind of set the stage here. I know Central Park is out of the region that many of you are from, but I think it's a good indication since it has a nice long record of precipitation data. And basically what I'm showing here is right up until the present, the 10 biggest one-day rainfall events in Central Park. And the ones that have the little raindrops next to them are ones that have occurred in the more recent years. You can see they're basically in the 2000s. I guess I stuck in that 1999 as being close to being 2000. But really the thing to note is the Central Park record goes all the way back to 1869. And if we look at these top rainfall events, 40% of them, 4 out of the top 10, have occurred in the most recent 15 years. So again, an indication that these bigger events are a more recent phenomena, especially when we look back at a 100-year record. And you can kind of get a smattering for what causes these events in the downstate New York area. Lots and lots of tropical storms. They're by far the main cause of these really big events. But there are a couple events that don't fall into that category. A summer convection event, nor'easters are obviously contributing to that as well. By looking a different place, again, maybe again outside of your region, but closer to me, and look at Syracuse, a shorter record going back only to about 1950, but the same type of picture that we see. In the top 10 events, 70% of them have occurred in the most recent 43% of the years. So kind of a little bit liberty going back to the 1990s there, but again, a higher percentage of these really big events occurring in recent years. This is something that we see across the country. So this is a graphic out of the last National Climate Assessment, and I use it just to point out that literally and figuratively, the Northeast sort of sticks out as a sore thumb in terms of seeing the biggest change in what they're calling very heavy rainfall events. And roughly these very heavy rainfall events in this case are defined as 2 inches in a day. So really across the country, except for Hawaii, all of these are positive. So there's been an increase through time since the late 1950s to the present. but the Northeast sticks out by almost having a double change compared to the Midwest and the Southeast, almost 3 times the Southeast, actually. Can look at that in a couple of different ways. Here's what I've done is look at the state of New York. I've looked at 2-inch rainfall events. Again, this is coming out of a state summary from the last climate assessment for the United States, NCA 4. And what you can see in this graph is each bar represents a 5-year period, and this is the number of days that have precipitation of 2 inches or more, averaged over the state. And you can definitely see since about 1990, these bars are pretty much the highest in the record. You have to go back to the 1900s to find one that's higher than the last 30 or so years. And the individual dots are not the 5-year periods, but they're the actual years. And you can see the greatest number averaged across the state, 1, 2, 3, 4 at least are the highest on record. Kind of that continues. If we look at the entire United States, you see a very similar picture. So this is not a Northeast or a New York specific phenomena. It's clearly what we see across the country, actually across the globe. But in a lot of cases, it's exacerbated. We see the bigger changes across the Northeast. I'm going to base most of my talk kind of on the type of data set that we're going to look at. It's something that's called the partial duration series, and it's used extensively in engineering design. If anybody's familiar with NOAA Atlas 14, which looks at rainfall extremes, this is generally the base data that go into there. And really, all it is it's station-based data. So if I have a station that has let's say 70 years of record, I find the 70 biggest rainfall events. So at this location, and I'll admit I forgot, I think it's Syracuse, excuse me. These are the highest one-day rainfall totals in the 70-year record at Syracuse. The ones in yellow are highlighted just to kind of say that you can have more than these in 1 year. So it's not that each have to come from a separate year. You can have multiple events. So as an example here at Syracuse, the second biggest rainfall total, this 4+ inch total, occurred in 2010. And then about a month later, there was over a 2.5 inch total in September. So you can have multiple events. Really, the whole basis for analyses like this, looking at saying, hey, what is going to be a storm that we expect to see every 25 years or every 100 years or every other year? It's really an exercise in statistics. And I'm not going to dive too much into statistics other than kind of saying we take these individual events. So you can kind of look at these blue bars, and that's really the rainfall totals from that partial duration series. And we fit a statistical distribution to it. So that's indicated by my red line there. And really the reason we do that is to kind of smooth out the sampling variability. Kind of why do I have the deck of cards up there is because I think there's a really good analogy, right? I only have 50 years of record, but I'm trying to figure out what the 100-year storm is. What's the probability of getting a storm once in 100 years? And in some ways, that's the same thing about maybe, not quite playing with a full deck, only having some of the cards and trying to figure out what the probability is of any of the poker hands that you might have. So if you can kind of follow that analogy, that's sort of what we're doing. And we do that by fitting this distribution. So the data kind of drives this theoretical kind of a distribution of rainfall totals. That's what's done in NOAA Atlas 14, a NOAA publication that's put out by NOAA themselves. Here's the example of it with a URL for New York State. So it's pretty much a point and click map. So I've chosen, I don't know, an arbitrary location in New York. And actually, I guess I've clicked on Liberty. And then NOAA gives you a bunch of information. So I'm going to kind of follow this lower line here. So really what this says is that if I'm looking at an event that covers a 24-hour duration, a one-day rainfall event. The data from this station says that you would expect to have at least 3.18 inches on average every other year, the 2-year storm. There's a 50% chance that that would occur in any given year. And then you might go out to an extreme, say 100 years, and same type of thing. That would say there's a 1% chance in any given year that you'll have 7.42 inches of rainfall in a day. Again, on average, a 7.5-inch rainfall event occurs once every 100 years. Kind of using that difference of a 1% chance and on average every 100 years, because really a lot of people kind of misconstrue what is meant by that 100-year storm. They kind of feel if I had the 100-year storm today, I'm not going to see it for another 100 years, but that's not the case. There's a 1% chance that that storm will occur in any given year. With the distribution fitting and statistics, NOAA can even go out to be a 1,000-year storm. Obviously, you have to make a bunch of assumptions there. And also in the parentheses down below these numbers, there's some uncertainty in this. Again, the analogy is I might have given you one deal of a deck of cards and you figured out the probability. But then if I shuffled the deck and gave you another deal, you'd probably get a different set of probabilities. And so really the real answer, the real probability lies in between these values. So that confidence interval in this case is really an artifact of the statistical fitting of the distribution. We know the data have occurred, but that's the uncertainty in going out to these, especially these longer timeframes. And I guess I kind of jumped the gun. That was kind of my clue to say that in my next slide here. So we can go on beyond that. The NOAA data has a number of different products. So here is a graphical product. And really, these types of graphical products are used very much in engineering design. So if you are working with the state DOT or with an engineering consulting firm, this is kind of the way that they would look at these extreme rainfall values. And lots of nice colors here, but let's just focus in on one part of the graph. I'm going to say this is the 24-hour storm, the one-day storm. So that gives me my duration. I have precipitation depth along the vertical axis. In many cases, these graphs will be intensity. So instead of just inches, it would be inches per some time period. But this one is depth. And then the different colors represent the different recurrence intervals. So if I wanted the 24-hour storm, for maybe the 100-year return period in the blue, that would give me my 7-inch value that we saw in the tables. Kind of just a graphical representation of all the numbers in those tables. And you can see kind of increases linearly for kind of the shorter durations, the sub-daily durations, but then really changes pretty quickly as you go out to longer durations, up to many days. So how have these kind of 100-year storm type rainfall statistics changed through time? This is some work we did actually quite a while ago. And the idea behind this is these are stations in New York. And what I've done is I've divided the period of record at these stations into kind of two chunks. I looked at a 1950 to 1979 period of record, and then a later period of record going through 2009. And why 2009 is, again, this is some older work. So that's the latest available data that we had. And then what I did was compared the return periods for the 100-year storm, the 50-year storm, and the 2-year storm based on data in those two short periods of time, the earlier period and the later period. And if nothing changed, these box plots basically would have their center points, these red lines, right up here at 100. It would say that, the percentage of one event is the same. There's a 1-to-1 match. But actually what we see is in the later period of time, all these red lines are much further down. And the way you would kind of interpret this and what these numbers represent is in the early part of the 1900s, from 1950 to 1979, what you might have considered to be the 100-year storm is really now the 66-year storm when you look at the more recent data. So since the rainfall frequencies, since these big rainfall events have increased, a storm that you would expect to see only once in 100 years, you now would expect to see once every 66 years. So almost, not quite, but almost double the frequency. Same type of thing with the 50-year storm. You would expect to see it 50 years, but in the more recent data record, that occurs every 33 years. Again, about, in round numbers, about a doubling of the frequency. And even the same thing for the 2-year storm. So these bigger rainfall events, something over the long-term record we'd expect to occur once in 100 years, we're seeing it much more frequently, and the data bear that out. Why does this occur? Or here's an example of how these change. I'm looking at, again, I picked Liberty, New York based on kind of its proximity. It's in the Delaware Basin, but also has a nice long period of record. And really what I'm showing here by the blue line is what the 100-year storm would have been if I stopped looking at the data in 1990, if I had my data period of record that extended to 1991. So in each of these cases, I add a more recent year to the data record. And you can see through time that this value has gone up. What might have been a 100-year storm in Liberty in 1990 would have been about 6.5 inches. By the time I got to 2010, it's about 7.25 inches. And that came up and really has kind of leveled off in the more recent years. And what's going on here is each of these really green bars represent events that are actually above, they're in the upper half of the biggest events that have occurred historically. So there has been a lot of these in recent years, and that affects this, in this case, the 100-year storm. And this comes out of a website. The URL is there. It's a product that we've put together actually for our work in New York. So any station, you can kind of see how these extremes have changed through time. And this is updated each year, basically. Not quite the 2024 data yet in this, but in a couple of months when that data is available, you could see what this would look like going through the most current rainfall data that are available. All right, so that's kind of sets the stage for what has happened in the recent past. Hopefully you all agree with me that these extremes have increased. But the real question that people are asking is, how will these continue to change in the future? How is this used in engineering design? It's like, maybe I'm building a culvert, and I want that culvert to, that culvert's going to last, that culvert pipe is going to last 50 years, and I don't want that area to flood in that period of time. So it really doesn't make sense to use that past period of record when we know the rainfall frequency is increasing. So we want to say, all right, how will this rainfall that's going to affect the size I need to build this culvert, what will that look like over the lifetime of the culvert that I'm building? So we do that using climate model projections. In the work we've done in the Delaware Basin, we've used 2 sets of projections. So basically, we have to go from the large global climate scale, so global climate models, down to a more localized resolution, and that's done with a process called downscaling. So we've done that 2 ways, or actually we've used data from folks who have done that 2 ways. One is a statistical method for doing that, which we call LOCA, and one is a dynamical method. And basically what it does is it nests a higher resolution model within the global models. There are 2 valid ways of doing it. They have their pros and cons, but really one is not better than the other, so we chose to use them both to kind of give an idea of what the range of uncertainty might be. And the models we use, particularly in the LOCA, were used in the National Climate Assessment, the NCA 4. One of the other things we have to worry about is how is society going to evolve? What are the greenhouse gas emissions going to look like? The extreme rainfall in 50 years really depends upon whether we do little to curb emissions. So that's that blue scenario where we're continuing to increase our emissions of CO2. Whether we maybe increase in the near term and start to stabilize, the red, that's what I'm going to call a lower emissions scenario, RCP 4.5. Whether we become really aggressive and kind of suck carbon dioxide out of the atmosphere in the green scenario. None of our simulations are based on that because that doesn't seem to be realistic, at least in the near term. And then, or maybe something more middle of the road. So basically in our current work, we're going to focus on the blue. I'm going to call that a high emissions scenario. And the red, I'm going to call that a low emissions scenario. So how does it work? Well, kind of a complicated graph, but real quickly, basically, just like we did with that partial duration series, we get partial duration series from the climate model projections. We grab 50 years of data from different time periods, both historical and future, and we fit our distribution. Then what do? We do some statistical resampling. So in other words, I have this distribution and I randomly pick events out of this to kind of sample the statistical variation. It's kind of where those confidence intervals come out in the Atlas 14 product that I showed. So we do that, actually we do that 1,000 times for each of the 47 models we looked at, each of the 2 greenhouse gas emissions scenarios we looked at, in each of 3 time periods that we looked at. So if you do the math, that's over 250,000 simulations. Then from each of these distributions, each of these lots of distributions, we find what value of precipitation, that's kind of where I'm moving my cursor up and down, corresponds to a different percentile. So in other words, the 100-year storm has a 1% chance of occurring or being exceeded. So I want to find the area under this curve that represents only 1% of the total area. And whatever that line represents, that's going to be the 100-year storm. So I do that and I capture that for both, say, the historical period that corresponds with what Atlas 14 uses, and then some future period. So either 2022 to 2070 to kind of sample the middle of this century, or 2050 to the end of the century to kind of represent the late century. And then I compute what we're going to call a change factor. It's this value for the future period divided by this value in the historical period. So it's kind of a ratio of what it was versus what it's going to be. So typically what we'll see is the historical period is going to be less than the future period. So this fraction is going to be a number bigger than 1. Keep in mind, I've done this a zillion times. So I have a whole bunch of these change factors. And then from that distribution of change factors, I can find the average and use that as a change factor to look at a projection into the future. Or if I want to be maybe a bit more conservative, I want to have a bigger extreme rainfall value. Might want to sample out here at one of these bigger change factors. Or perhaps if I'm, really I don't care much about the risk. The project doesn't matter that much. I'm more concerned with cost, perhaps. I'm going to still factor in that the climate is changing, but I might use one of these change factors that is smaller, has a lower chance of occurring. So how does that look? I focused in on New Jersey from some work we've done there. And each of the dots represent a grid point in these downscaled data sets that we've been using. If you focus on the middle, that's the median. So going back, it's computing all of these change factors and picking the median value, the median change factor. And then they're basically color-coded. So I'm looking at the 2-year storm. I'm looking at the median. And basically the colors represent the change factor. So if I'm somewheres up here, again, in the Delaware watershed in extreme southeastern New York, most of these dots are this kind of grayish color, which says that in the future, and I forget, I'm missing a spot in my chart here. I believe this is I believe this is middle of the century, 2020 to 2070. I need to inflate the current Atlas 14 value by somewhere between 15 and 20%. So in that example of Liberty, where it said the 2-year storm was, I forget what it was, 3 inches. If I want to prorate that to the future, I need to multiply 3 inches by 1.2. So I need to make that something like 3.6 inches to account for the climate change. The range, the uncertainty, is actually quite large. So for New Jersey, they wanted to do the 17th and the 83rd percentile to actually match their sea level rise projections for some reason. And so if we use that at the low end, the smaller adjustment has a 17% chance of occurring. In most places in southeastern New York, it's about, between 7.5% and 10%. On the high end, in most places in northeastern New York, it's actually up on the order of 25 to 35%. So that kind of gives you the range of uncertainty in some of these projections. The 2-year storm isn't that extreme. You expect to have it every year. So actually, it's a lot easier to look at that in terms of maybe something like the 100-year storm. So I'm doing the same thing, but for the 100-year storm, again, the idea here in most of southeastern New York, the adjustment for the 100-year storm is different than the 2-year storm. And actually, it's more on the order of about 30%. So on average, if I want to look at the 100-year storm 50 years into the future, I need to take the Atlas 14 value and multiply it by 1.3, make it 30% higher. The 100-year storm, it's way out there on the tail of the distribution, so it's harder to estimate. If I want to look at what the range of this adjustment is, can do that as well. And you can see a lot more colors and a lot more lower colors. So across New Jersey and even up into New York, boy, those we barely have a difference. This kind of Band-Aid color is a 2.5 to a 5.5% increase. So much smaller on the low end. If I go to the high end, some of these adjustment factors are huge. I actually have to change my color bar because I didn't have enough color. And these bright pinks and things like that are on the order of like 50 or 60%. So a very, very extreme adjustment for the 100-year storm. Plausible. Some of the models are saying that. Some of the scenarios are saying that. But again, in most cases, folks are using the median for most of their planning. Kind of say, what is the difference of the emissions scenario? So I'm looking at the 100-year storm at the end of the century, and the difference between these two graphs is whether I'm at high emissions or low emissions. So again, if I focus in on an area here under the low emissions scenario, we see changes that are on the order of, again, that 15 to 20% in the median under the low emissions. But then when I go up to the higher emissions, the 8.5, I'm back up to that really dark color. We're in the 30% range. So this emission scenario almost changes this change factor by 15% in what we're doing. So really how society is going to play out is part of what we need to look at for how these changes and extremes are going to come about. Many people ask me about durations that are less than a day. That's very important for stormwater management in urban environments and things like that. These big summer type cloudburst events and things like that. Unfortunately, the climate models are not good at simulating rainfall at sub-daily resolutions. Basically the time step in most of these models is 1 day. They make a number of assumptions to kind of account for shorter term rainfall, but they're really just estimates. So what we've looked here is looked at a handful of models that do have sub-daily data to see what are these change factors for a 1 hour event or a 6 hour event compared to a daily event. So I'm looking at high emissions. I'm looking out at the end of the century. I'm looking at the 100-year storm. And, you see a lot of variation. So even to start off with the 1 day versus the 24-hour, you would expect these to be pretty much the same thing. They're representing the same period. But when I add up those hourly values, I don't get quite the same thing. If I look through the different values, I get a lot of kind of spurious results that move around and no real consistency in what I might expect. It's a lot higher for 3 hours. It's less for 6 hours. It's back up higher for 12 hours. And it's really different for 24 hours. So basically that was the long way of saying in any of our work, we've chosen to apply our 1 day adjustment to any sub-daily duration. There's just not enough information to go on. And really, there's really the 1 day value is really within the range of uncertainty in any of these sub-daily values. So kind of bringing it down, that's the data, that's the analysis, and kind of looking at how do we present this as information to a user. So for the Delaware River Basin Commission, we've created a website. I think that's what caught Paul and some of the other people who encouraged me to give this talk attention. The URL is there. And basically the way the website is developed, it accounts for all counties that touch the Delaware River Basin Commission. So that's why several of the New York counties are included in our work. The black is the outline of the basin, and obviously the counties are in the green here. And basically the site allows you to select whether you want to look at counties or municipalities or basins. That's what a HUC 12 is. Allows you to choose between the two emission scenarios, a time period that you're interested in, and then the exceedance probability. Again, 50% is a 2-year storm, 10% would be a 10-year storm, 2% would be a 50-year storm, 1% would be a 100-year storm. So in the example I'm looking at here, I'm on the county, I'm in a low emission scenario, kind of the middle of this century for the 2-year storm. All of the counties are shaded in green, which basically say it's about a 10% increase to the Atlas 14 value. If I click in the same type of map here, I've made a few changes here. I've chosen to look at the municipality level. So a lot smaller spatial agreements here, both in New York and within the rest of the basin. I'm looking at high emissions. I'm still looking at mid-century, and I've chose the 100-year storm. So if I look at some place maybe down along here in New York, I'm looking at more maybe about a 22 or a 25% increase in the Atlas 14 value for mid-century 100-year storm. I can change this again, and now I'm trying to think what I did. I went to the end of the century instead of the middle of the century. So more time has gone out, more climate change has been manifested. The map looks a lot more bluer. If I look in these areas in New York, we're almost up to 30 or more percent. Kind of goes back, and remember those dot maps that I show, that's kind of how that comes onto this sort of nicer map and website type of view. The map is clickable. So I've chosen to click on, I went back to the county level, high emissions, mid-century 100-year storm. I've clicked on Ulster County. And when I do that, I get a little bit of a change in the presentation here. The first thing is the change factors kind of come up here in a tabular form. So instead of this green color, I can actually see for Ulster County, the median change factor is about 14%, 1.4. I see the range of plausible change factors, right? The smallest change factor, 10% of the change factors are actually less than 0.93. 17% of the change factors are less than 1. So some of the models, some of the scenarios say that there's not going to be much change in extreme rainfall. The lion's share, say that there's going to be an increase. And the highest 10% say the increase could be as much as 1.44. By clicking on a county, you also get one of these graphics, again, that the engineering community uses quite a bit. It gives you depth versus duration. And it shows the actual Atlas 14 values. By clicking on this map, I can actually go to the Atlas 14 product and get the Atlas 14 values and display those on the map. And then in the blue line, it shows that Atlas 14 value inflated by the median change factor. So if you did the math here, and there's some tooltips when you're actually on the site, you can see that the value for Atlas 14, if I multiply that by 1.14, I'll get the blue line here. We see that for many different durations. The site also allows you to toggle on and off the confidence intervals. And to give you an example take that back. The site also gives you the option to get tabular data. So you could look at the 24-hour storm at this location in Ulster County. The Atlas 14 value is 9.59 for the 100-year storm there. The projected value with that increase is about 10.9. So again, you can do the math. It's at really applying that 1.14 conversion factor. The site also gives you some idea of the uncertainty. So what I'm showing here is, again, the green is the actual Atlas 14 value. If you were an engineer designing something in Atlas in Ulster County, those would be the rainfall values you would use in your design if you weren't factoring in climate change. The blue is that median value from the Atlas, from the website. And the blue shaded area says, all right, how do these confidence intervals affect this value? So I'm looking at actually in this case, I have toggled on the 83% confidence interval. So it's basically looking at the 17% smallest change factor and the 83% highest, that range of the distribution. And the thing to note in this case, and why I use this as an example, is the Atlas 14 value falls below that. So kind of even though there's this large range of uncertainty in the change factors for the 100-year storm, in 83% of the cases, they exceed what the current design would be based on Atlas 14. And I believe with that, a couple of other things here to kind of tie things up. This idea of getting data and turning it into information needs to be transparent. The results and what we did have to be well vetted, and we've definitely done that for our work in the Delaware River Basin, both with our own technical reports and reports that have been peer-reviewed in the literature. They also need to be updatable. Climate is changing. So an atlas that we put together last year doesn't really say much about what might happen in the future. Not only does more precipitation data change, but the climate models get updated. So as a quick example here, all of the work that's been done so far in the Delaware Basin and in the Mid-Atlantic region have been based on what's known as the CMIP-5 generation of climate models. Very recently, within the last year, there's been a new generation of climate models. We've yet to do any work that has incorporated these into our change factors. There is some work afoot to do that for the entire state of New York with some work with some resources that we have from the state. So that's something to look for in the future. We've done a little bit of work specifically for New York City itself. And the idea here is I'm looking at change factors for the different rain return periods based on the old CMIPS 5 model. So basically for New York City, really these change factors for the 100-year to the 2-year storm are somewhere between 10 and 20%. But when I recalculate those based on the newer generation of climate models, the red line, we see that's much higher. So the take-home message here is the new climate models tend to be saying that our adjustments may need to be larger than they were in the older climate models. Wouldn't read too much into this yet. It's a very limited area over New York City. I don't know if that will hold broader for the state or for the region, but nonetheless, something we need to look at. And also really have to tackle this idea of, do the change factors that apply to daily rainfall actually also apply to hourly rainfall? Again, some New York City work that we did kind of showed that the hourly change factors in the observed record were changing much, much, much quicker than the daily record. And that was kind of concerning in a way that, you know, these 1 hour events were changing at a much faster rate. But I wouldn't get too apprehensive about that because when we've looked broader across the country, that doesn't seem to hold. And this actually seems to be something that's very localized to the stations around Central Park and actually driven by, we think, by Ida and the big hourly event that occurred right before that. So those two really, really record-breaking events that occurred in the very end of the record seem to be skewing that for hourly at Central Park, but not for the broader region or not for the broader part of the state. And with that, open it up to questions.
Great, thanks so much, Art. That was so helpful for kind of demystifying the statistics around extreme precipitation.
Hopefully it demystified it and didn't make it worse.
Well, it helped me for sure. And I just want to apologize to everyone about the chat at the beginning, and thanks to Hannah for opening it up. My apologies. Okay, so the questions are rolling in. And right off the top, you know, we know that a 100-year event has a 1% chance, and you were mentioning 66-year event. So what's the percentage to that? It's always confusing, I think.
Yeah, I would say a 66-year storm has a, I'm going to do the numbers real quick here, right? So the 60, it has about a 1.5% chance of occurring in any given year.
Great.
Right? A 50-year storm has a 2% chance. So round numbers, about a 1.5% chance. So you have that extra 0.5%. That might not sound much in any given year, but when you start to say, all right, you know, what is the chance of that happening in a 30-year period or something like that? That does become a lot more, oh, wow, I might see this, you know, the chance of seeing a 100-year storm twice in 30 years is actually is higher than you would think. You know, think about flipping a coin, and you know, you can flip a coin many times. You don't expect, you know, heads to come up, you know, 50% of the time, but if you did it 4 times, in many cases heads might come up all of those 4 times, and that really has a low percent, but you kind of see that happen. So the more times you see that, it kind of inflates the chances of that occurring.
Okay. So have you heard of anyone else that's using the tool that you created for the Delaware River Basin? Yeah, anyone else using that tool?
They're using it extensively within the basin for anything that the basin is managing. So any of the municipalities within the basin are indeed using those inflation factors. The entire state of New Jersey through the DEP is using that. That's basically in their regulations that not the Delaware River Basin tool, but a similar tool, similar work that we did focused on New Jersey itself. Those values are coming into play. And also the other state that's using it quite a bit is, again, not the Delaware River Basin tool, but the same methodology as Virginia. So they factored that into any of their engineering design for transportation projects.
Great. And what are some of the biggest challenges you encounter when doing these types of analyses?
Yeah, I would argue the uncertainty and
Mhm.
conveying the uncertainty to people, right? You know, you might say, well, Art, you said, 10% of the time there's a 10% chance that, wow, this 100-year storm's even going to be less. And yep, that's absolutely right. But it is a small percentage, and kind of getting lost in the weeds is a hard thing to convey. In my mind, it's clear that extreme rainfall is increasing. It's clear that extreme rainfall is going to continue to increase as the climate warms. It basically, if it didn't, it would pretty much defy the laws of physics. So it's kind of a given that it has to occur. And it's a matter of, in implementing the design, just how risk adverse you are. I don't think it's a good idea to use the old data that's clearly from a period of time when the rainfall record was very different than it is today. So, factoring that in and embracing that is quite useful, actually.
Great. And so how often are these IDF curves, DDF curves updated? And I know that there's an Atlas 15 coming out in a couple years. They're working on it. So do you have any insights on that?
Yeah, they're working on it. So I mean, kind of again, it's the example of things are changing. When we started our work with extreme precipitation, probably back in the probably around 2010 or whatever, the data that were used in the predecessor of Atlas 14 were older than I was at the time. So basically, all the engineering design was based on data that was 50 years old in 2010, which, boy, isn't a good idea. So in a lot of our work, kind of especially in the Northeast, kind of, I think, spurred our colleagues in NOAA to update it to create Atlas 14. And then a lot of our work with looking at these change factors, I kind of like to believe led some of NOAA's decisions to more broadly look at Atlas 15. I don't know where Atlas 15 is going to stand. Atlas 15 is basically due to come out in kind of two slugs. The first slug is just really going to be looking at the observed data. So it's not going to include anything in terms of projections. They're going to use a little bit different methodology than they've had in the past that does account for the trend in the observed data, but only the trend up until whenever they decide to publish Atlas 15. The next installation of Atlas 15, the next part, will include the projections. I'll admit, I don't know where that's going to stand in the current political climate with things, whether that project will move forward or not. I have not heard that it's not, but I do question, that is a thought that's in the back of my mind. So this idea of bringing in projections is planned for Atlas 15, but not in the first installment of Atlas 15.
Great. Yeah, thank you for that clarification. We did get a request from the chat if you could put up your first slide.
My first slide.
And we have a question about local data.
Like that one or my RCC slide?
Oh, I'm not sure.
I don't know.
Yeah, maybe they can add it to the chat.
Okay.
So were the so we have Mohonk Preserve a really long record here. And question was, were the historical precipitation kept by them incorporated into this data?
There is a long-term site in Mohonk, and yes, that's part of the Atlas 14 database, so that does come into play. One of the things that is done in the current Atlas 14, particularly in the part of the state that you're from, they really scoured all of the available historical data when they did that. And as a result, there are many stations that were in existence, kind of in around Greene and Ulster and that part of the Delaware Basin that had fairly short records, like back in the 30s and 40s. And they were used. And really, those stations really present a very different picture of that region than the more current record or the stations that have a longer term period of record. So there is some, that's one part of the state where Atlas 14, in a lot of cases, looks very different from if you're only using stations that have at least 50 years of data and data from 1950 forward. So I'm not even like going to the more recent period in the 2000s. I'm going all the way back to 1950. You see a difference there from looking at stations there versus short periods of record early than that. And that kind of skews the Atlas 14 values in the Catskills quite a bit, actually.
Great. We've got 1 minute. The questions are really rolling in. So I think we have time for maybe 1 or 2 more. And it is the opening partner slide, if you could put that up on the screen.
Yep.
Thank you. And so can you comment on how these projected increases in rainfall intensity translate to increases in stream flow?
Not really. It's a complicated relationship, and it has to do with it's not a one-to-one. So if I say the rainfall goes up 10%, the stream flow doesn't go up 10%. There is work being done to try to do the same things with stream flow records. But clearly there, particularly in southeastern New York, in the Catskills, in the Delaware Basin, a lot of the stream flow is being based, it relies on soil moisture, it relies on snowpack. So there are other changes that come into play other than rainfall that affect those areas.
Great. And then real quick, is there a relationship between these rain events and drought frequency?
Not really. I would say they are two phenomena. I would say at some broad scale, there is a relationship because, how do I want to say it? Really what you tend to see is the current literature on climate change sort of says like weather patterns tend to get a little bit more stagnant, and the troughs and ridges that you might picture on a weather map tend to become deeper for needs a lot more time to go into those regions. So based on that, there are some reasons why you could say with that as an underlying factor in both drought and extreme rainfall, you do see those changes. So, the current thinking is drought frequency does also increase with climate change. It's not like you would expect to see things like the 60s drought more frequently, but you may expect to see these kind of short-term 1-2 month droughts more frequently. Again, this year was a good example with what we might have seen as we moved into the fall, where we had a very, 2 months that were really dry, record dry Octobers. And, things changed around quickly after that, but we still had a drought impact there, especially with fires and things like that.
Yeah, great. Well, not great, but thank you. Thank you so much for your time. And we're a little over, so I'm gonna end it there and say thank you all for joining. I'll send out some information afterwards, and yeah, have a great weekend.
All right. Thank you, everyone.
Bye-bye.